Greetings and welcome to the complete lecture for Chapter 6 of Chemistry 221, which is called The Composition of Substances and Solutions. And we're going to see here that there's a lot of utility that a chemist can get out of a solution. And knowing about the composition of different things can certainly help a chemist as well. And you can see the poor cave people there that are trying to determine the formula for the dirt molecule. Oh, I have a strange sense of humor. It cracks me up. But without any further ado, let's check out this chapter and see what it has to offer. In this chapter, we'll talk about formula mass. And the formula mass, which is used a lot for covalent molecules, is just the sum of the average atomic masses of the atoms in the substance's formula. And basically, the formula mass is also equal to the molar mass, which we saw earlier, the grams per mole in a molecule. So for covalent molecules with non-metal compounds, the formula mass is literally just the mass of the molecule. No big deal. Here's an example of chloroform. Chloroform is CHCl3, and the molecular mass, which is the mass of an individual molecule, is the same number as the molar mass, which is the grams per mole when you have a mole of things, which is what chemists usually use. And to figure this out, you'd have 1 carbon, 1 hydrogen, and 3 chlorines. And those values there are listed to the hundredths on the periodic table, which are great for most of the time. When you add them all up together, it's 119.37 grams per mole. So we would call 119.37 grams per mole the molar mass of the compound, and that's also equal to the formula mass because CHCl3 comes in individual molecules, so the formula is 119.37. And again, that number is pretty cool because it represents the average mass of one molecule, if it's AMU, which is very, very small amounts of grams. But what's more useful to chemists is the molar mass, which is grams per mole. That's the grams in a mole of the compound. So in a mole, you have 6.022 times 10 to the 23rd molecules. So the number is the same. If you change the units, you can have a molecule's mass or a mass of grams in a mole of the substance. They're both really cool. For ionic substances, though, it's a little bit different. In an ionic compound, you don't really have discrete molecules, but you do have smallest units that repeat each other over and over again to have like an empirical formula, if you will. So for sodium chloride, in the lower right-hand corner, that kind of cubic thing, that's really what happens when you have sodium and chlorines next to each other. It's not an individual sodium and an individual chlorine, but it's repeating NaCl, NaCl, NaCl. And it's all 3 dimensions, up, right, left, forward, back, all those different ways. So chemists refer to the formula mass of sodium chloride as having 1 Na and 1 Cl, and that's the molar mass. Now, honestly, this is kind of a nitpicky thing that we're not going to worry about too much, but just realize that with ionic compounds, you've got lots and lots of them kind of smashed together. And when we find the molar mass, it's really the mass of one formula unit. It's like 1 Na and 1 Cl. But in reality, you have a whole bunch of them going on, but all the rules still apply and no problem. So if you can find molar mass for a compound, you're good to go, whether it's covalent or, in this case, ionic. If you want to determine an empirical and molecular formula, that can be important, and definitely for chemists, because one of the ways that chemists get paid is, what is this formula, all right? And so we'll talk a little bit in this section now about percent composition. Now, percents in chemistry are usually percents by mass, which means how many grams are in something. So when you see a percent composition with a number next to it, in 100 grams, you'd have that many grams of the compound, stuff like that. As an example of what I mean by this, let's talk about ethanol, which is C2H6O. And ethanol is drinking alcohol. That's nothing you need to know, but it is kind of interesting. So ethanol has carbon, hydrogen, and oxygen. It has 2 carbons, 6 hydrogens, and 1 oxygen. But when you want to find the percent composition, it's 52.13% carbon, 13.15% hydrogen, and 34.72% oxygens. Now, a couple of things about this. First of all, notice that if you have the percentages of all the different elements in a compound, they should equal 100%, or by sig figs be pretty gosh darn close to 100%, if you know what I'm saying. Second thing is that a formula is a mole-based ratio. So in a formula, C2H6O, that's 2 moles of carbon for every 6 moles of hydrogen for every 1 mole of oxygen. It's not the mass values, like it's not 52.13 grams of carbon for a formula. We have 2 moles. So formulas are based on moles, and percentages are usually based on mass. And it would be nice to know how to go from a mass percent to a ratio formula, and it would be nice to know how to go from a mole-based formula back to a mass percent, and we'll talk about that in this section. So here's an example of how we can make this work. Let's say we have a 10-gram sample of a compound, and in the compound it has 2.5 grams of hydrogen and 7.5 grams of carbon. Let's find the percentage by mass for both hydrogen and carbon. And this may be kind of simple for some of you. If it is, I apologize, but I want to make sure we're all on the same page here, so let's talk about it. Well, percent by mass is always going to be the grams of what you're looking at divided by the total mass times 100%. So for hydrogen here, we have 2.5 grams of hydrogen, and there's 10 grams total. So 2.5 over 10 would be the ratio, if you will, of hydrogen to the compound. Let's multiply it by 100%. 25% hydrogen is found in this compound. And you can do the same thing for carbon. It would be the grams of carbon divided by the total grams of the compound. So in this case, 7.5 divided by 10 times 100, 75% carbon. And again, both of those percentages together should be about 100%, and they are obviously. Also notice that if you wanted to feel kind of lazy, if you had the 25% carbon, percent by carbon, start again. Also notice that if you had the first value and you were 25% hydrogen and you were feeling kind of lazy, you could have just taken 100% minus the percent hydrogen to find the percent carbon. So 100 minus 25% would give you 75% carbon, which is exactly what we found. So there's different ways to play these, and it's nice to know all the tools you have under your belt. Use the one that's best for you. If you know the formula, you can also find the percentages and all that kind of stuff too. And what you should do is first of all find the molar mass of the whole compound. So let's use water as an example to find the percent composition of oxygen and hydrogen in this case. So what I would do is first find the molar mass, and water is 18.02 grams per mole. So in the oxygen, there is 1 oxygen in H2O. So 1 oxygen on the periodic table is 16.00 grams per mole. If you look up the actual value in the periodic table, it probably has more sig figs, but to the hundredths place, that's 16.00 grams of oxygen in a mole. And we'll divide that by 18.02 grams of water in a mole. If you cut out the moles, it's just 16 grams of oxygen in 18.02 grams of water. Multiply it by 100%. 88.79% oxygen. Cool. Now for hydrogen, it's the same thing. You would take the 2 hydrogens because it's H2O, and to the hundredths, hydrogen is 1.01. So you'd have 2 times 1.01 to reflect the 2 hydrogens in H2O, but you'd still divide it by 18.02 grams per mole. That'll give you the percent of hydrogen, and the way I've done it there, it's 11.2%. Now notice if you wanted to get sig fig crazy on me, which is actually pretty cool, you could go 100 minus 88.79. 100% is an absolute definition. Don't have to worry about sig figs. Minus 88.79 would give you a better sig fig percent. It would come out to be 11.21%. So there's different ways of doing things, and you will get different numbers of sig figs. Think about that as you go through your values. But either way is fine. So again, if you want to find elemental composition from a formula, first find the molar mass, in this case 18.02, and then the grams of the oxygen go on top, divided by molar mass to find percent oxygen. And for hydrogen, it would be grams of the hydrogen. 2 times hydrogen would be 2 times 1.01, divide by molar mass times 100. Good to go. So here's a question you might see. What's the percent nitrogen in nitrogen monoxide? Now, the molar mass of nitrogen monoxide is 30.01 grams per mole. That's a nitrogen plus a oxygen to get that number. So percent nitrogen, we would take the grams of N in NO. There's 1 N, nitrogen on the periodic table, 14.01 grams per mole. We'd put that in the numerator. In the denominator, you'd put the molar mass, 30.01. So 14.01 divided by 30.01 times 100%. Put that in your calculator or just watch me answer it. Either way is fine. Anyway, it comes out to be answer B, 46.68%. So nitrogen monoxide is 46.68% nitrogen. And if you wanted to know percent oxygen, you could go 100 minus 46.68. I think that's answer D, 53.32, if I'm not mistaken. Anyway, this is how these things roll. Pretty chill if you want to go from one to the other. If you want to know an empirical formula from the masses of things, you can do that too. And the general idea is you want to first convert the element masses to moles, because in a formula, you're always going to have moles. You're not going to have grams. So you've got to turn grams into moles. Then you'll have moles of at least 2 different elements probably. So you'll take the bigger one and divide it by the smaller one. And that you're looking for whole numbers, all right? So if you end up with a whole number, you're good to go. Sometimes, though, you'll end up with weird fractions like 1.5, and you can't have 1.5 atoms, so you'll need to multiply by some integer to give the smallest whole number value. Now, I'm sure that's not the clearest, so let's look at an actual example. Let's say that we have a compound, and it's found to have 1.71 grams of carbon and 0.287 grams of hydrogen. Let's use that information to find the empirical formula. Well, again, in a formula, you have to have moles. So you've got to turn the grams of carbon into moles of carbon and the grams of hydrogen into moles of hydrogen. Carbon is about 12.01 grams per mole, so 1.17 grams divided by the molar mass, 0.142 moles of carbon. If you do the same thing for hydrogen, 0.287 divided by 1.008 grams per mole, that gets you 0.284 moles of hydrogen. And at this point, you do have like a rough formula. It would be C.142 H.284. But that's pretty ugly. All right, that's not a formula like we've talked about in class so far. So to get it into a whole number ratio, you divide both of these numbers by the smaller number. So 0.142 is smaller than 0.284. So you'll divide both of those numbers by 0.142. 0.142 divided by 0.142 is, of course, 1, so that's nice. And 0.284 divided by 0.142 is a ratio of 2. So we have 1 carbon, 2 hydrogens. The empirical formula of this molecule, CH2, and that's kind of cool. Now, it's not the final molecular formula. We'll talk about that in a little bit. But if you have the masses, you can easily find the empirical formula, grams to moles. Compare them. If you need to, multiply by something. Empirical formula. Now here's another example with chlorine and oxygen. So we've got so many grams of Cl, so many grams of oxygen. Let's find the empirical formula. So like before, grams to moles is the first thing for both chlorine and oxygen. So chlorine, if you do this, chlorine is 35.45. So 5.31 divided by 35.45 gets you 0.150 moles of chlorine. And this would be a good thing to practice to make sure you can get this. I'm going to start kind of cheesing over some of the details because I want you to be able to do this yourself. And likewise for oxygen, 8.40 divided by 16.00, that'll get you 0.525 moles of oxygen. So see if you can do this yourself. Make sure you're good. But what this means then is you have 0.150 moles of Cl for every 0.525 moles of oxygen. Now that's an ugly ratio once again. So we'll divide divide both of those numbers by the smallest number, which is 0.150. So 0.150 divided by itself is 1, no problem. But oxygen here, we get 0.525 divided by 0.150, and that comes out to be almost exactly 3.5. So what this is telling you is that for every 1 chlorine, you have 3.5 oxygens, but you can't have a half oxygen molecule. That just doesn't roll in chemistry. You can only have whole numbers. So what you could do in this case is multiply the 1 and the 3.5 by 2. Having a whole number, super important in chemistry when it comes to formulas. So instead of having 1 to 3.5, multiply both of them by 2. It's like taking that whole formula and taking it twice. If you do that, you get Cl2O7, and those are whole numbers. Chemists can deal with that, all right? You can find molar masses, blah, blah, blah. So for this molecule, the empirical formula is Cl2O7. So if you see one of these weird fractions, just think about multiplying everything by a whole number, good to go. So here's kind of the general idea of what you want to do. And with that last example with Cl and O, that's exactly what I did. We started on the far left with grams of Cl and grams of O. We then divided by the molar mass to get moles of Cl and moles of O. And that was an ugly formula, but what you want to do then is divide both of them by the smallest number. So we divided them both by 0.150 to get a 3.50 to 1 mole chlorine ratio. And that's better, but we want to have whole numbers, so we multiplied both of those by 2 to get Cl2O7, the empirical formula in that plan. And if you can follow this, you absolutely have this process down. It's not too hard, it takes a little bit of practice, but it's nothing you can't do. And if you get stuck or anything, you let me know, or let the Learning Success / Avid Center people know too. We're all here to help you. We will definitely make sure you got this nailed down. So here's another example. And this example, though, we're going to start with percentages, mass percentages, and we're going to turn that into an empirical formula. So in the last example, we had grams of oxygen and grams of chlorine. We turned them into the empirical formula. In this kind of problem, we have percentages, and we're going to turn percentages into an empirical formula. And the only real difference is that if you have percentages, you want to assume you have a 100-gram sample. So that way the percentages become grams. You can then take the grams, turn them into moles by dividing by the molar mass. You'll get 2 mole amounts. You'll divide the smaller by both of them to try and get at least the first one a whole number, and the second one will hopefully be a whole number. But if it's not, you can multiply everything through to get whole number atoms, because remember, chemists like whole number atoms. So in this example, we're going to look at some kind of a bacterial fermentation of grain, and we end up with a gas which is 27.29% carbon and 72.71% oxygen. And the question is, what's the empirical formula of this gas? So again, the general idea will be assume 100 grams, grams to moles, compare the moles, multiply by some kind of number if we have to get whole numbers. Good to go. In this problem, if you assume 100 grams, that would be 27.29 grams of carbon and 72.71 grams of oxygen. So that's why I like 100 grams. Yes, you can use 1 gram. You'd have 0.2729 grams of C and 0.7271 grams of O, but I don't usually think that way. The easier, the better for me, but you could do that if you want to. It's no problem. So in my version, 100 grams total, 27.29 grams, 72.71 grams of O. Good to go. So when you turn the grams to moles, 27.29 grams of C divided by 12.01 grams per mole gives you 2.272 moles of carbon, and 72.71 grams of oxygen divided by the molar mass of O, 4.544 moles of oxygen. So at this point, you have a formula. It's C 2.272 O 4.544, but that's really messy. Divide both of those numbers by the smaller number, which in this case is the 2.272 number. When you do that, 2.272 divided by itself is 1, 4.544 divided by 2.272 is 2, empirical formula CO2. So this is carbon dioxide, which has been created. So this is the idea with percentages. Percentages assume 100 grams to grams, grams to moles, compare the moles. Good to go. Empirical formula is an interesting concept because some compounds have the same empirical formula, and if they have the same empirical formula, they'll have the same mass percentages. So as an example of this, nitrogen dioxide is NO2, and dinitrogen tetraoxide is N2O4. Now, if you take the empirical formula of both of those, empirical formula of NO2 is just NO2, but empirical formula, which is the smallest whole number ratio of N2O4, you can divide both those numbers by 2, for example, also NO2. And when you calculate the percentages, they come out to be the same way. So when a chemist calculates an empirical formula, especially for a covalent molecule, that may or may not be the final result because N2O4 is a lot different than NO2. NO2 is a brown, deadly gas. N2O4 is a colorless gas. I'm not going to say it's good for you, but it wouldn't kill you like NO2 would, needless to say. So chemists need a way to convert an empirical formula into a molecular formula. And what chemists do is they compare the molar mass of this. So if you take the molar mass and you divide by the empirical formula molar mass, you'll find that there's going to be a certain whole number ratio n that relates the two of them together. So the molecular formula will equal this empirical formula taken to the n times. And the n value can be found by comparing the molar mass of the whole molecule compared to the molar mass of the empirical formula. And it's easier than it sounds. It's hard to explain, but it's actually pretty chill. So let me show you an example of that. Let's say that we have an empirical formula of CH2O, and when you find the molar mass of that empirical formula, i.e. add up a carbon, 2 hydrogens, and an oxygen, it's like 12 plus 2 times 1 plus 16, that's cheesy sig figs, but it works, 30 grams per mole, 30 AMU. Well, the molecular molar mass of the whole molecule is 180 AMUs. So we can use this information to find the molecular formula of this compound. And again, we need to know the number of times the empirical formula will go into the molecular formula. And we can figure that value out by taking the molar mass of the whole thing and dividing by the molar mass of the empirical formula. So in this case, that ratio is going to be 180, which is the mass of per molecule, and we'll divide it by 30, the mass of a formula unit, those smallest empirical formulas. So 180 divided by 30 is 6. That means that there's 6 empirical formulas in the molecular formula. So the molecular formula would be CH2O taken 6 times. So if you multiply all of those things through by 6, you get C6H12O6. That's the molecular formula of this compound. Now, these ratios here are always going to be whole numbers. When we went from like percentages to empirical formulas, sometimes we multiply by 2 or something like that. These formulas will always be whole numbers. So if you get a value of like 5.99 or 6.01, just call it 6 and you're good to go. It's always going to be a whole number. Here's a question. Glyceraldehyde is the compound with an empirical formula of CH2O and the molar mass 90.08 grams per mole. What is the molecular formula of glyceraldehyde? All right, no problem. So to figure this out, we need the ratio. We need to know how many empirical formulas are in the molecular formula. And to do that, we need to find the molar mass of the empirical formula. So if you add up 1 C, 2 H's, and 1 O, it's like 1 times 12 for carbon, plus 2 times 1 for hydrogen, plus 1 times 16 for oxygen. Again, you can use kind of cheesy sig figs here because that ratio is always going to be a whole number. So you add up 12 plus 2 plus 16, it comes out to be 30 grams per mole. The empirical formula is molar mass. And 90 grams per mole, the whole thing, divided by 30 grams per mole, the empirical formula, 90 divided by 30 is 3. So the molecular formula will be CH2O taken 3 times, or the C3H6O3 value. So down there, you can see what I did. I found the empirical formula's molar mass, and just cheesy sig figs works because the ratio you're going to get Always a whole number. And in this case, the ratio is almost exactly 3. That ratio of 3, you multiply by the empirical formula to find the molecular formula. So CH2O taken 3 times will give you the answer here, C3H6O. So pretty chill. Let's do a combined question now, where we start with a compound with mass percentages, and we also know the molar mass of the whole compound. So from this, we want to find the empirical formula and then the molecular formula. And I would encourage you to try this on your own. Okay, you've got all the skills to do this. So I've got the answers along the way. If you don't get these answers, then let me know and stuff. We can figure it out. But to answer this question, first of all, we have 81.10% boron, and it says the compound has just boron and hydrogen. So what that means then is 100% minus 81.10, that'll give you the percent hydrogen. And those percentages, just assume 100 grams, so that would be 81.10 grams of boron, and I think you have 18.90 grams of hydrogen, if my math is done right here in my head. And you would turn those grams of elements into moles, so 81.10 grams of boron divided by the molar mass of boron gives you that 7.502 mole boron number. Do the same thing for hydrogen to get 18.75. Now, if you compare those values, you would divide both 7.502 and 18.75 by the smaller number, 7.502. Initially, it looks like you're going to get boron 1 and hydrogen 2.5, but you can't have fractions. I only have whole numbers. So if you multiply them both by 2, the empirical formula, B2H5. That's the empirical formula, smallest whole number. Now, next thing you need, molar mass of the empirical formula. So 2 borons and 5 hydrogens gives you a molar mass of 26.67. Now, the whole molar mass is 53.3 grams per mole. So 53.3 divided by 26.67 will always give you a whole number. Looks like it comes out to be 2. So the empirical formula twice will give you the molecular formula. So B2H5 taken twice gives you B4H10. Good to go. So try this on your own. See what you do. If you get stuck, let me know. Happy to help. All stuff you can handle. We're now going to shift gears and go from the composition of compounds into the composition of solutions. And solutions are really important in chemistry because a lot of times chemicals will react better as solutions than they will in their solid phase or their liquid phase. And to understand solutions, we must talk about what's called molarity. So let's just first talk about what a solution is and then go from there. Now, in the real world, you don't have that many pure compounds. Usually things are come in mixtures, all right? And a solution is a type of a mixture. It's an homogeneous mixture, which means you'll mix some things together and it looks like you have just one single phase. So as an example of that, let's say you took sugar, which is a solid, you can see it, and water, and you mixed them together to make a sugar solution. Well, it's homogeneous because it looks just like water still. It doesn't look like you have solid particles moving around or anything. So homogeneous mixture means that when you mix these things together, it looks like you have just one substance, but in reality, you have more than one. Now, if you mix these things well, and you always should, and it's usually not too hard to do, you'll have a uniform composition, all right, which means that the solution at the top will have the same values as the solution on the bottom. But to describe the composition, scientists will use the concentration term, and that's where molarity will kick in. Now, solutions do have two components. They're called the solvent and the solute. And the solvent is the component that physical state is preserved when you mix them together. So if you mix things with water, which is what we'll do most of the time in this class, the solvent phase, the liquid phase, is what the solution will look like. But the solute is really the more exciting part, all right? So that's the part that's usually present in a lower concentration, but this is why we're making this solution. So for example, hydrochloric acid is water plus HCl, but we don't call it a water solution. We call it a hydrochloric acid solution because the HCl is the exciting part. And earlier I talked about the sugar solution. Sugar is exciting, all right? You take a swig of that, you're like, whoa, you know it compared to water, right? It's that sweet, syrupy kind of sweet taste anyway. So the solute is the exciting part, the sugar in the sugar solution, but water is the component that actually is usually preserved as you go through. An aqueous solution is something where water is the solvent, and that's what we're going to focus on most of Chem 221 through Chem 223. And if you have an aqueous solution, it's going to get the symbol AQ, and I'll show you examples of that here in a little bit. So solutions, pretty cool, not only to us as human beings, but also to chemists. And if you see that AQ, that just means that water is your solvent. Now, molarity is a way to talk about how concentrated your solution is. So let's say you're making those sugar solutions and you put just a little bit of sugar in versus a lot of sugar in, and it's the same amount of water. Well, the little bit of sugar, when you taste it, will be sweet, but when you taste the one with lots of sugar, it'll be, make your mouth power up. Anyway, my mouth is doing gymnastics right now. It's hard, you can't tell, but anyway, it's crazy. Anyway, the sugary sweet will have a really powerful taste, while the not a lot of sugar will be a lot less. So chemists will talk about these with molarity, and molarity is the moles of solute per liter of solution. And molarity is just a number. So like if you saw 3.6 m, that would be 3.6 molarity, which means 3.6 moles of solute in a liter of solution. So if you had a sugar solution that was 3.6 m, you'd have 3.6 moles of sugar in a liter of solution. But you could also have a 0.036 molar solution, and that would be 0.036 moles of sugar in a liter of solution. So that sugary sweet solution would be more like 3.6 m, and if you didn't have a lot of sugar, that would be possibly 0.036 m. So the number tells you how much solute is present. It's really helpful to chemists. This is by far the dominant concentration form. We'll talk about other concentration forms later, but you always have a solute. You add it to the solvent to make the solution. Water is usually our solvent, not always, but usually. Pretty chill. And now we can describe how much solute is in our solution, which is also cool too.
To prepare a solution of known concentration, we must first weigh the solute. We need an accurate volumetric flask designed to hold 250 milliliters. We first add the solute to the empty flask. The flask is filled about halfway with water and mixed to dissolve the solute. We add water in stages. Combining all the solvent with the undissolved solute in one step can lead to inaccurate measurements. We mix again. The solution is prepared.
This is the typical method that's used to create a solution. What they'll do is, first of all, you need to know how much solute you're adding to how much solvent. And in this case, they're adding 5 grams of nickel 2 chloride hexahydrate. This is a hydrated compound we talked about in chapter 3, no big deal. We're going to add that to enough water to make 250 milliliters of solution. And by the way, notice in the video how they measured from the bottom of the meniscus. So the meniscus is like the bottom of the curve of water. So chemists will usually measure the volume to the bottom right there, and that's the official way to do it. Now you want to make sure that all the solute dissolves, because unless the solute dissolves, you don't really have a solution. So they added about half the water, stirred it up so all the solid dissolved, and then they added the rest of the water so the bottom of that meniscus was right at that line. That's a 250 milliliter graduated cylinder, so that's a pretty accurate version of it. Anyway, let's say we make the solution perfectly. We can use this information to calculate molarity. So that big M is always moles of solute over liters of solution. So when this problem, to calculate molarity, we need to turn grams of the NiCl2.6H2O into moles. We also need to turn milliliters into liters. And by the way, 1,000 milliliters per liter will be a really helpful conversion for you on this, so make sure that you know it. So anyway, we'll find the molar mass of nickel 2 chloride hexahydrate. And when you do that, it's a nickel plus 2 Cls plus 6 waters. And when you do all that, 237.7 grams per mole. So 5 grams divided by the molar mass gives you the moles of the solute. We're also going to convert milliliters into liters. So 250 milliliters divided by 1,000 milliliters per liter is 0.250 liters. So the molarity, moles over liters, comes out to be 0.0841 molar, or that big M is what molar is. Sometimes you'll see it listed like this, where the solute is in square brackets, and it will equal then a number of molarity. Either way is great. You'll see it both ways. Now you're the hip chemist and can know what it is. So every liter of this solution would have 0.0841 moles of nickel 2 chloride hexahydrate. But you can see that we don't have a liter of solution. We have only 0.250 liters. So we'll talk about ways to extract the moles from the volume you add here in a little bit. In this example, we want to know what mass of oxalic acid, which is a compound you can get at the store or something like that. Oxalic acid has the formula H2C2O4. How much oxalic acid do we need to make 250 milliliters of a 0.0500 molar solution? So in this kind of problem, we know how much we need, how much volume we need, and we know the concentration, but we don't know how much of the solute to add to the volume to make that concentration. So it's an easy kind of problem to do. Molarity is moles over liters. So moles over liters times liters will give you moles. And that's what we're going to do on this problem. We're going to solve for the moles of oxalic acid that we need. That's going to be molarity times the volume in liters. And from the moles, you can find, using molar mass, you can find the grams of oxalic acid needed. Now remember, it's 1,000 milliliters per liter. So in this case, 250 milliliters is 0.250 liters. And if you multiply that by the big M is moles per liter. So the liters on top and the liters on the bottom cancel. 0.0125 moles of oxalic acid are needed. So if you had the molar mass of oxalic acid, which you can get from the periodic table, 2 hydrogens, 2 carbons, and 4 oxygens, that comes out to be 90.00 grams per mole. And if you multiply that by the moles you need, it turns out we need 1.13 grams of oxalic acid. If we add that to 250 milliliters of water, we'll have a 0.0500 molar solution. So this is kind of a cool way to make a solution if you know the concentration and the volume that you need.
To prepare our solution using the dilution method, we first obtain 2 milliliters of stock solution with a pipette. Filling the pipette with stock solution to the mark on the pipette ensures that we have 2 milliliters of this solution. We add the 2 milliliters of more concentrated solution to the 500 milliliter volumetric flask, touching the side of the flask with the pipette. We add water to the mark on the flask. After mixing thoroughly, we have exactly 500 milliliters of a solution with a concentration of 1.60 times 10 to the minus 4 moles per liter.
So when you're making a solution, oftentimes what chemists will do is they'll weigh out so much solid, find the mass, put it in so much volume to find the concentration, et cetera, which is no problem. And you can find how much solute you need, like we saw in the last example, if you know the volume and concentration. There's all different variations. But believe it or not, it's also very common to take a concentrated solution and add water to it to give a concentration which is less concentrated. A lot of the acids and bases that we use here at Mount Hood Community College come as very strong concentrations, like HCl, sulfuric acid, sodium hydroxide. And what we'll do is we'll add water to it to make a solution which is more manageable. The pure acids and pure bases are so strong, they'll burn through things and do lots of things that we don't want to have happen, especially if it's like a lab where you're just beginning. So if you add water to it, you can then figure out what is going on. Now, Now, when you add water to a system, the solution color usually changes. And so both in the video on the left and in these copper 2 solutions on the right, notice that as you add water, the color becomes less intense. So in the video, that orange became kind of a yellow. In the copper 2 solutions, the dark blue copper 2 became more dilute, like a lighter blue. And this is also very common. It's not all the time the case, but a lot of times you'll see that. So just keep that in the back of your mind. To figure out how much water you need to add, a lot of times chemists will use this expression, which is C1V1 equals C2V2. And there's lots of variations on this. So I used to use M1V1 equals M2V2. Sometimes you'll see MIVI equals MFVF. But the idea is that you have a certain concentration that you begin with and a certain volume. And you want to dilute the concentration to a new volume, V2. What is the new concentration C2 going to be? And you could do the same thing with M's and V's, whatever you want to. But the idea here is, remember that volume is usually in liters and concentration is moles per liter. So the moles that you begin with, the 1 values, equal the moles that you end with, the 2 values. So you're not changing the moles, you're just changing the concentration by adding or subtracting water, something like that. So let's look at an example. Let's say we had 0.850 liters of a 5.00 molar copper 2 nitrate solution, and we're going to place that in a 1.80 liters through the addition of water. So the question is, what is our new molarity? All right. Now notice in this problem, we started with 0.850 liters and we ended with 1.80 liters. So that means you're going to add something like 0.95 liters of water. It's not that you're adding 1.80 liters to 0.850 liters. That's an important designation to make, and we'll talk about that here in a little bit. So in this question, we're just taking the 0.850 liters and adding enough water to make 1.80 liters. We can use this to find the new concentration. In this problem, 8.850 liters, that's V1. That's the initial volume. And C1 is 5.00 molar. So you can probably see then that 1.80 liters, that's going to be V2. We're going to solve for C2. So in this case, C2 will be C1 times V1 divided by V2. So it'll be 5.00 molar times 0.850 liters. We'll divide it by 1.80 liters. This comes out to be 0.236 molar. So our new solution is 2.36 moles per liter, which makes sense because we added more water, etc., etc. And again, note down there that we added 0.950 liters of water to make this happen. We didn't add an extra 1.80, we added 0.950 liters to make the old volume up to 1.80 liters. So here's a question you might see. We have 20 milliliters of 3 molar HCl, and this student apparently accidentally added it to 100 milliliters of water. So the total volume is 120 milliliters. What's the new concentration of HCl? And this kind of stuff happens intentionally and unintentionally. It's no big deal. But the good news is you can figure out what it is using that C1V1 equals C2V2. So in this question, C1 is 3.00 molar. Now, you could convert all of the volumes to liters, but as long as the volume units are the same, you can keep them in milliliters. So I'm going to use V1 as 20.0 milliliters and V2, the total volume, 120 milliliters. So it's going to be 3.00 times 20 divided by 120, and if you do that, you should get 0.500 moles per liter, answer D. So again, as long as the volume units are the same, you can keep them in milliliters. You don't have to go to liters. There's nothing wrong with going to liters, but why not make it easier on yourself and just keep it in the simplest unit possible? There are other units used for solution concentrations, and we'll talk about those later on. But some ones that are kind of important that pop up once in a while are mass percentage, volume percentage, and parts per million. So we're not going to talk super deep about those right now, but I do want to talk about them, what they are. A mass percent, which is usually solute, will be mass of the component, the solute, divided by mass of the whole solution times 100%. And if you see one of of those. It's just something you can deal with. Sometimes it's easier to figure out mass percent than molarity, but honestly, molarity is cooler in my opinion. Now, a volume percentage will be a volume of solute divided by volume of the solution times 100%. These are usually for very specialized procedures, but they do pop in once in a while. Again, they're both percentage. Most of the time in our classes, all the percentages will be mass-based, so they would measure out how much what the component you have in relative to how many grams of the solution you have. But if you do see these, this is what they mean. Here's an example of a mass percentage. Let's say you had 5 grams of a sample, and in that sample you had 3.75 milligrams of glucose. What is the mass percent of the glucose? So this would be grams of the solute glucose divided by total grams of sample times 100%. But notice here we have milligrams. Well, the sample is in grams, so I would convert one into the other. It's probably easier to go milligrams to grams. There's 1,000 milligrams per grams, so 3.75 divided by 1,000 would be the grams of glucose. We'll divide that by the grams of the spinal fluid, which is crazy, and then we'll multiply that by 100%. This comes out to be 0.075% glucose. If you see that, that's what this means. It doesn't happen a lot, but it does happen sometimes. Now you're in the know. Here's an example of a problem too. In this one, we're looking for a volume percentage. So in this question, 50 milliliters of ethylene glycol are added to a radiator with 120 milliliters of water. So you'd have a total volume of 170 milliliters. What's the volume percentage of ethylene glycol? So that'll be the 50 milliliters of ethylene glycol divided by the total volume times 100%. If you do that, it comes out to be 29.4%. Again, we're not going to use mass percentages and volume percentages like this a lot, but if you see them, it's good to know how to handle them. They're pretty chill once you kind of know what's going on. A type of unit you might come in contact with more often is what's called a parts per million. And a part per million, and also the equivalent parts per billion, parts per trillion even sometimes, are used for very low solute concentrations. So if you ever looked at environmental work, like environmental studies, or sometimes the government will use this when talking about water purity, stuff like that, parts per million are used. Now, parts per million is probably the most common, but again, you can have parts per billion, parts per trillion, stuff like that as well. Now, a lot of times these are based in water-based solutions, and they assume for these that the density of water is just 1.00 grams per milliliter, and that can be useful and confusing to the chemist sometimes, but just kind of FYI about that. So in this case, a parts per million would be the mass of the solute, what you're looking at, divided by mass of everything times a million. A million is 10 to the 6. A million has 6 zeros, so that would be 1 with 6 zeros. That's where the million comes from. So parts per billion, same concept, but with 10 to the 9th instead of 10 to the 6th. So parts per million, parts per billion, used for small concentrations of solute. If this solute is a pollutant or a poison to people, then it might be really important. So let's say we have some kind of pollutant. It's 5 milligrams present in 100 grams total. Let's calculate this in parts per million. Now, in order to do this, we need to turn milligrams into grams. And again, there's 1,000 milligrams in 1 gram. So we'll do that first before multiplying by a million. So in this case, 5 milligrams, you divide by 1,000 to turn that into grams. That would be grams of solute, or the mass of solute. We'll divide it by 100 grams total of the solute present and multiply by a million. So if you do this, this comes out to 50 parts per million. So this pollutant is present in 50 parts per million under these cases. Again, it can be useful. It's a very, very small amount, so a lot of times pure chemists don't worry about it, but it's nice to be able to translate this kind of work into things that make sense in terms of molarity and stuff like that. Okay, so that's the end of chapter 6. It's kind of cool to see how these formulas come around and also talk about molarity. Molarity will follow us all the way through Chem 223. There's definitely more assistance for you if you need any help on it, and you can definitely reach out to me as well if you have any questions. I'm more than happy to talk about this. All right, thank you so much for spending your time with me. I hope this has been helpful, and I hope you have a wonderful day.